Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
On the frontiers of space in the shuttle Columbia, and working far below the surface of the Earth in oil well drill pipe, in applications as demanding as turbocharger impellers, and as simple as bicycle forks. A rapidly growing number of parts are being fabricated through the technique of inertia welding. All of these parts were manufactured by the process of inertia welding. The principle is simple. Indeed, it is not unlike that of the blacksmith's forge. But if the process is simple, its benefits are great, and its applications as broad as the engineer's imagination. Inertia welding can dramatically reduce parts cost, join dissimilar metals, boost production, reduce inventory requirements, cut lead times, and virtually eliminate waste. How does inertia welding work? Basically, by forcing together pieces to be joined in such a way that rotary motion and pressure are converted into heat, which literally bonds the pieces into one part. Two pieces to be joined are aligned in an inertia welding machine. One piece is held stationary. The other is rotated rapidly on a spindle chuck attached to a flywheel. When the flywheel reaches a predetermined speed, it is disengaged and the freewheeling piece is forced against the stationary piece. Friction between the parts heats the budding surfaces to forging temperature. Just before rotation ceases, the two pieces bond automatically. When the flywheel stops, the weld is complete. The two pieces are now one part. The process you have just seen can be described graphically. The spindle chuck flywheel assembly is accelerated to a preset speed, usually called the welding speed. At this point, the external drive motor is disengaged and the pieces are forced together. Friction between the parts slows the flywheel, converting the stored energy to heat. The heat generated is enough to soften, but not melt, the interfaces. After an initial rise, upset, the displacement of metal, remains fairly constant during the heating phase. While axial pressure remains constant, the speed continues to decline, and just before rotation stops, the parts are bonded. The remaining energy still in the flywheel forges the weld zone, expelling impurities in the form of flash, and at the same time refining the grain structure of the bond. The weld is complete when the flywheel stops. Axial pressure is discontinued after a short dwell period. There are only two variables during inertia welding. One is speed, which determines the energy level. The second is the axial weld force, which determines the rate of energy conversion. Both of these have been determined for many materials, and geometric combinations and welding parameters are easily calculated. For some material combinations, it is advantageous to use a step pressure program. This capability is standard on all inertia welding machines. Inertia welding is an advanced variation of the friction welding process. Traditional continuous drive friction welding, sometimes referred to as direct drive, utilizes the same principle, creating heat by friction between the two budding faces. But instead of using stored flywheel energy, it employs a direct motor drive to the rotating part. The piece to be welded is accelerated to a constant speed. At the same time, moderate axial force is applied, generating friction and heating the interfaces relatively slowly. When the heat reaches the desired forging temperature, which is usually controlled by a timer, the driving motor is declutched and a brake is applied to stop rotation as quickly as possible. This time is called the rundown time. The point at which the driving motor is declutched can also be determined by using a preset shortening of the parts, or a burn-off length. Axial pressure, normally called forge pressure, is increased. At that time, a large percentage of flash is forced out of the weld joint. Another timer controls the duration of the forge pressure. Direct drive friction welding differs from inertia welding in that direct drive welding has more variables which need to be set and monitored during the weld cycle. In addition to high production rates and superior bonding, inertia welding has many other advantages over conventional welding processes. They include lower energy requirements, no need for filler materials, flux, or other consumables such as shielding gases, consistent quality, and forged weld joints. Because it is an automatic machine-controlled cycle, inertia welding also offers freedom from operator control. And because upset is so consistent, length lost being typically 15% of the workpiece diameter, upset can be used to check product quality. For quality control purposes, electronic machine monitors check and compare the set parameters against the actual performance of the machine. Flash is normally smooth, and if it has no adverse functional or appearance effect, it can be left on the part. When necessary, flash is usually removed after the part has been removed from the inertia welder by turning or routine machining. However, if the additional cycle time is warranted, flash can be removed on the machine by turning or by automatic flash strippers. This photomicrograph shows the coarse grain structure and wide heat-affected zones typical of metal melting in a flash butt weld. By contrast, this inertia weld of the same materials shows both mechanical mixing and grain refinement. Here, metal mixing is shown in an inertia weld between 1040 steel on the left and GMR 235 superalloy. Many different metals can be joined by inertia welding. Among these are a variety of carbon, alloy, mar aging, stainless, and tool steels, copper, brass, and some bronzes, aluminum and many aluminum alloys, titanium and titanium alloys, nickel, cobalt, and alloys, refractory materials, dispersion-strengthened materials, and sintered materials. In addition to these, recent work has led to the successful joining of precious to base metals. Inertia welding is singularly effective in joining dissimilar metals. This electrical connector was inertia welded from copper and aluminum components. A bimetallic electrode demonstrates successful welding of titanium and copper. This pump motor shaft is made using stainless and carbon steel components. Because of the plasticizing and forging nature of inertia welding, surfaces to be joined need only minimal preparation. As long as the mating surfaces are reasonably flat and clean, they may be sawn, sheared, or flame cut, and even welded as forged if scale is not heavy. Even dirty and oily surfaces may be welded. The residue simply burns off during the welding process. Most inertia weld joints, no matter how complex, are a variation of one or more of 6 basic types. Bar to bar, tube to tube, bar to tube, bar to plate, tube to plate, and tube to disc. Let us examine a few diverse applications of these principles to inertia welding. Nearly every aerospace manufacturer in the free world employs inertia welding in the manufacture of components. The F-14 fighter bomber uses several inertia welded parts. Manufacturing Technology built the welder for the Rocketdyne division of Rockwell International, manufacturer of the Columbia's engines. Inertia welding was found to be virtually the only practicable method of welding the 600 closely grouped injector posts on the mammoth main engines of the Space Shuttle Columbia. Each weld of the cobalt-based alloy posts to the Inconel 718 stubs was accomplished in less than 5 seconds. Jet engine manufacturers, GE, Pratt & Whitney, Rolls-Royce, and others use inertia welders to join turbine and compressor components. At GE, this Model 400 is making a 24-inch diameter compressor ring assembly of Inco 718 nickel alloy. 2 more welds are made to complete the 4-piece assembly. Compared to one-piece forged design, material savings per assembly are 370 pounds of nickel alloy. Other welding methods researched could not yield consistent quality. A new generation of machines especially designed for the aerospace industry are shown here during installation checkout proceedings. This Model 480 can weld up to 36-inch diameter rotor components and has a weld force of 426 tons. Caterpillar Tractor Company has employed inertia welding since 1966 in the manufacture of components for its heavy-duty construction equipment. More than 500 part numbers are inertia welded, of which some examples are track roller brackets, formerly made as a casting, track rollers, pre-combustion chambers, filter housings, and pin assemblies. This machine, the Model 700 inertia welder, can weld up to 7-inch solid rods and has a capacity of over 70 square inches in tubular steel. The available weld force is 750 tons. Caterpillar Tractor Company is using this, the largest machine ever made, for the manufacture of hydraulic piston rods and other hydraulic components. In over 10 years of service, inertia welded rods have proven to be just as reliable as solid forged rods. Another place where inertia welders helped solve a problem is in the outboard motor industry. Manufacturers including Evinrude, Mercury, and Chrysler Outboard use inertia welding to fabricate a variety of components, including propeller shafts. The propeller shaft must resist corrosion, but the end in the gearbox must be wear resistant. Stainless steel is used at one end, carburized and hardened steel at the other. The inertia welder joins these parts quicker at less cost. Ford, General Motors, Saab, Mercedes-Benz, and Alfa Romeo are among the automobile manufacturers now using turbocharging to extract more performance from fuel-efficient gasoline and diesel engines. This turbocharger rotor is one of many which is inertia welded by most of the turbocharger manufacturers in the world, including Air Research, KKK of Germany, and Schwitzer. The materials used in this rotor are 713C and SAE 4140. The same welding concept is employed in the manufacture of turbine components. Production times are typically 30% less than the times required by traditional welding techniques. Inertia welded parts do not have to be exotic to be interesting and technically challenging. This proto-tool ratchet wrench body, formerly a one-piece forging, now comprised of a sintered steel head and a screw machine steel handle, was welded on a manufacturing technology Model 120 inertia welder. Bicycle forks may not suggest high technology, but they too can benefit from the cost savings and strength of inertia welding. Schwinn manufactures fork stem assemblies on a Model 90 inertia welder. Oil and water well drill pipe must be utterly reliable. Problems which occur thousands of feet underground can be enormously expensive. Most major manufacturers of drill pipe, including Hughes Tool, Monismon, Drillco, and others, use manufacturing technology inertia welders to assure necessary weld strength and consistency. Shown here is a Model 250BX inertia welder welding tool joints to 30-foot pipe sections. With automatic pipe handling equipment, welds on a 4.5-inch pipe with a weld area of about 7 square inches can be made in less than 50 seconds, floor-to-floor time. Once an oil well has been drilled, the oil must be lifted to the surface. A string of sucker rods is used to connect the pump mechanism above ground to the actual oil well below ground. On this Model 180BX inertia welder, thread connections are joined to the sucker rod ends for a strong and reliable bond. Applications of inertia welding abound in the trucking industry. One of these is the fabrication of trailer brake cams by Fruhoff. Formerly forged in one piece, the cams are now inertia welded on a Model 250 machine at a rate of 60 per hour, reducing forging inventory and cutting part costs by 24%. This oil pump gear, formerly a machine forging, was inertia welded faster and more economically from 3 pieces of bar stock. The task is completed on this Model 180B inertia welder with rather innovative tooling. The operator manually loads 3 pieces in the machine, one journal in the spindle, and the other journal and gear blank in the tailstock. After cycle initiation, the machine automatically makes the first weld, unclamps the tailstock, and indexes the second journal into welding position. Each cycle produces one piece part consisting of 2 welds, saving valuable handling time. A simple automatic unloading device further saves operator time. Engine valves of all sizes are joined by inertia welding. For the valve head, a heat-resistant alloy is needed, while the valve stem can be made from a less expensive material. Inertia welding solves this problem fast and reliably. Most valve manufacturers use fully automated machines in an inline machine operation. Production rates will vary from 500 to 1,200 pieces per hour, depending upon diameter and if single or dual spindle machines are used. This model, Dual 60, produces 1,200 pieces per hour, having a stem diameter of 312 thousandths inches. This Model 90 inertia welder is not only automated, but it also removes the weld flash by shearing it off in a second operation while the flash is still hot. In this fashion, no weld time is wasted for flash removal, and a production rate of 450 pieces per hour can be maintained. In another automotive application, a transmission part is automatically welded at a rate of 300 pieces per hour. If the standard machines do not fit the application, manufacturing technology will design and build machines which are best suited for the job. This application was to join 3 mounting nuts to a transmission cover. A single spindle machine would have to make 3 separate welds per cover, which was time-consuming and would have required 9 machines to satisfy the customer's production requirements. By combining 3 spindles in a cluster, each weld is made independently of the other, but at the same time. Only 3 machines were needed, producing 360 covers per hour, per machine. In another unique application, a 3-piece assembly had to be joined by inertia welding, trapping a washer between a cup and threaded stud without sacrificing weld strength or production rate of 600 pieces per hour. The solution was a Model 90 inertia welder with a 6-station indexing unit, combined with hopper and vibratory loading equipment. To demonstrate the function of the machine, you're seeing here a graphic top view of the indexing table and spindle. The stud is being loaded into the tailstock fixture. After 2 indexes, the washer is loaded over the stud and secured by 2 spring-loaded levers. At the same time, at another station, the cup is pushed into the tailstock fixture. Again, after indexing, this cup is transferred from the tailstock fixture into the spindle. While the tailstock rotates the stud washer assembly into the weld station, the spindle accelerates, holding the cup securely. After reaching speed, the weld is made, trapping the washer permanently between the cup and stud. The welded assembly is removed via an unloading arm at the rear of the machine. This is the actual machine in motion, elevating the parts to the vibratory bowls and loading chutes, loading the stud, washer, cup, transferring the cup, welding, and unloading. For odd-shaped parts which cannot be readily loaded into the welder, another solution had to be found. This Model 180B inertia welder, one of several supplied to Dana Corporation, has automated spindle and tailstock tooling. The shape of the parts makes it necessary to present the clevis to the spindle in an oriented manner, such that the chuck can accept them for secure clamping. A 4-position indexing table which can be loaded by the operator will present the parts to a loading arm. Should one of the stations be empty, the arm and table go into a search pattern looking for parts. The tailstock tooling includes a walking beam mechanism which loads the rod from a loading chute and unloads the welded assembly in the same cycle. One outstanding characteristic of manufacturing technology inertia welders is their flexibility. Because many inertia welders are used in job shop environments, machine adaptability and fast changeover are necessary for profitable operation. Not only can manufacturing technology welders be automated in a variety of ways for quantity production, they also can be readily adapted for a variety of welding requirements. For example, all manufacturing technology welders feature flywheels made in rings, which can be changed to accommodate the inertia requirements of different materials. All machines feature easily adjustable speed and pressure settings to meet the requirements of each application, thus enabling the user to join a wide range of part sizes and material combinations.
This is the finished part. Well, that looks good. I had another question, though, about the stroke of the internal shear.
We have 15 inches available on the ID piston. We introduce hydraulic
Manufacturing
fluid at the rear of the
technology
piston.
consults with the manufacturers, designers, and engineers, both in product design and in the development or adaptation of inertia welding equipment best suited to meet product and production requirements. Machines are designed, fabricated, and assembled at Manufacturing Technology's Mishawaka, Indiana plant, and at its sister operation, Adams Engineering in South Bend, Indiana. Manufacturing Technology operates its own job shop for inertia welding of parts on a contract basis and has laboratory machines available for sample and prototype welding in addition to feasibility studies. A spare parts inventory valued at more than $500,000 permits fast delivery service to equipment customers throughout the world. Inertia welding, a technologically advanced, efficient, and effective method of fabricating large and small parts, is proving itself every day in a variety of new applications. Its future is limitless, a challenge to the designer's imagination and an answer to many of his problems.